Okay, nuclear fission. So basically in 1939, Hahn and Strassmann discovered that when you bombard uranium, so a lump of uranium or a uranium atom, when you bombard it with neutrons, you just draw a neutron like that, when you bombard it with neutrons, basically the uranium nucleus will split. So if this is the nucleus of the uranium, the nucleus can split, and it will split into two nuclei of a similar mass, and also you will get two neutrons released in the process. Okay, now the main important feature about this happening is that apart from the fact that there are two new elements created out of that one, a lot of energy is given off. Now the energy is in the form of the kinetic energy of the two what are known as daughter nuclei. Okay, so there's a huge amount of energy released when the nucleus of uranium basically splits up after a neutron being fired into it. Okay, large amounts of energy and of the order of 200 electron volts, which really doesn't mean a lot to you guys right now until we go into it. Okay, so the details of uranium fission in order to help you to understand how a nuclear reactor works. Okay, so uranium, when it is mined naturally, uranium is found, natural uranium is made up of two types of uranium. Now, 0.7% of it is made up of uranium-235, and 99.3% of the natural uranium found in the ground is uranium-238. Okay? Now, there are two isotopes of uranium. Obviously, 92 is what's identified as uranium, 92 protons. Okay, important facts. If uranium-235, this guy, if this one is bombarded with either slow or fast moving neutrons, if you fire neutrons at this one, it will undergo fission. It will split into the two daughter nuclei with the release of energy and with the release of a couple of neutrons. Okay, that's whether it's bombarded with slow or fast moving electrons. The formula for that is uranium, or one of the formulas. It doesn't always give you the exact same daughter nuclei. So uranium-235 plus a neutron, so basically it captures a neutron and then splits, gives you Ba144 and 56. The 56 is what identifies it, plus kryptonite, I think it is, 3690, and you get your two neutrons as well. Okay, that would be one equation for nuclear fission of uranium-235. Okay, now if you, so two neutrons, effectively that means that's two of these, so maybe it's better to write it like that. If you add all these numbers here, you'll get the same as the sum of these, and if you add these, you'll get the same as this. Okay, now it is more likely, 235 is far more likely to undergo fission if it's bombarded with slow moving neutrons. So slow moving neutrons are preferred, and it'll be more likely that you'll have fission if you have a slow moving neutron entering the uranium. I think it has to be comparable to the kinetic energy of the neutron that's bombarding has to be comparable to the energy, the average energy of the neutrons in the uranium nucleus. Okay, or the surrounding average kinetic energy of the atoms. the surrounding atoms. Okay, the products are often called daughter nuclei, or fission fragments is another word for them, so to be aware of that. And these are often radioactive themselves and can spit out alpha particles or beta particles, radiation gamma. Okay, the energy that's given off in this reaction is the energy of these two, mostly moving, kinetic energy. All right. The neutrons that are released, these neutrons are fast moving. Okay, and that's important because you have fast moving neutrons released, but preferably it is slow moving neutrons that will make the 235 further atoms of 235 split again into daughter nuclei like that. In other words, the fast moving electrons are less likely to cause further atoms of 235 to undergo fission. Okay, right, now if at least one neutron from each atom that undergoes fission, so a uranium-235 undergoes fission, and remember you get 2 neutrons released. If at least one of those neutrons causes further fission in another atom of 235, okay, remember, you have billions of atoms together in a lump of uranium. So if that neutron causes further fission in another atom of uranium-235, then and for subsequent ones, if one neutron at least coming out of this, when this one splits, if one neutron coming out of that causes further fission, then you have what's called a chain reaction. Okay? And effectively it is kept going. The reaction is kept going and lots of energy is released. Okay? Now, if you have a small mass of the uranium, it can be too small for a chain reaction to occur. 1 second now. Okay. The neutrons will escape. So if you have a small mass of uranium, okay, then you will not have a chain reaction because the mass is too small. There's too few uranium-235 atoms in here, and they're producing fast-moving neutrons, and the fast-moving neutrons are less likely to cause fission. However, if you have a critical mass, in other words, if you put 2 masses together to create a larger mass, then in the larger mass, you will get a chain reaction. Okay, so no chain reaction when the mass of uranium is below a critical level. If you increase the mass, you can have a chain reaction, and that is what a nuclear bomb is. Effectively, you have in a nuclear bomb, you have 2 masses of uranium that are below the critical mass. A mini explosion pushes the 2 together to create the mass that you want, and then that causes a nuclear chain reaction within here, and energy is released. Huge amounts of energy are released, and that is a nuclear bomb. Okay. Okay. Uranium-235 is the atom, or is the element, the isotope of uranium that is used for a nuclear bomb. Plutonium is another one, plutonium-239, which will also undergo fission with either slow-moving or fast-moving neutrons. Okay? Right, a nuclear reactor. I'm going to do that in a different video actually. But the main key things to take out of this are, preferably uranium-235 needs slow-moving neutrons to cause fission. Uranium-235 is only found in a very small amount in naturally mined uranium. So if you mine uranium naturally, only 0.7% of it is uranium-235. The remainder is uranium-238, and uranium-238 will not undergo nuclear fission. Okay.